So valence bond theory rests on this idea of hybridization. Let's look at what that is a little bit deeper because I've just kind of thrown that word at you. And let's look at this through the example of carbon. Now we know that carbon has 4 valence electrons, and that we were saying because it has those 4 valence electrons, it would need to form 4 bonds to be able to experience an octet, right? And that's how we were handling things with Lewis theory. But now, if we take that idea with Lewis theory and look at the electronic structure of that carbon atom, they don't work together. So here I have the orbital diagram for carbon. And when we built this, when we were talking about filling in our electrons and kind of placing them within the orbital structure in an orbital diagram, we said, okay, well, our 2s electrons are going to pair up together, and then our p orbitals are at a higher energy level because they have that node, that planar node. And so those will fill second, and so we'll put 2 electrons in our p orbitals. So what we really have here are 2 unpaired electrons. And we've said that a bond is created when we have overlapping orbitals that have 1 electron each that then pair up. So looking at this picture, we really have only 2 unpaired electrons that can participate in a bond. And they're p ones, right? And remember our p orbitals, we've got in our x, y, z plane, we've got one in the z plane, one in the x plane, and one in the y plane. Shade these in. So if we have 2 unpaired electrons, we've got probably one in one of our p orbitals and one in another. That would create only 2 opportunities to form a bond with another atom. And so we can imagine it here in the one that I have xed off, that we would have one of our electrons on our carbon would be in this p orbital right here. Another one would be right here. And it would be matching up with an electron from each of these hydrogens. And so the picture that we have from our orbital diagrams, and this idea of bonding being 1 electron and 2 orbitals overlapping to form a covalent bond, would predict that carbon would only form 2 bonds, 2 single bonds, and that they would be at a 90-degree angle to each other. And so in this picture, we can't have a octet achieved. This orbital right here is going to stay empty unless it overlaps with something that has 2 electrons in an orbital, right? And so this doesn't give us a picture at all of what we see in terms of carbon bonding. This is because Lewis' structure wasn't really, like the Lewis theory wasn't really designed to explain and predict based off of our idea of what a modern atom looks like, or our modern picture of an atom. Not that atoms have changed. So how do we get this picture of carbon has to have all 4 of its valence electrons be able to participate in a bond to be able to hit its octet? And so what happens is, if we think of our atomic orbitals, when the carbon is totally isolated on its own, it can make sense. But when that carbon is coming into contact with other hydrogen atoms, it's going to have the opportunity for those valence electrons to interact with the valence electrons of those hydrogens. And those those atomic orbitals are going to hybridize to maximize the stability that would be gained by bonding to 4 hydrogen atoms. And so that hybridization happens right here. What happens is that that 2s, and those 3 2p orbitals, they all combine to make an sp3 set of hybridized orbitals, where each one has 1 electron and they're all at the same energy level. Then you can see we have 4 unpaired electrons, and we can then have 4 connections to another atom that has an unpaired electron to make that bond, which would then create an octet once the actual bonding takes place. So valence bond theory is going to predict that carbon would have 4 things bonded to it, whereas just Lewis theory in combination with our understanding of the atom would only predict 2 things. But what is required to make this happen is mixing those 2s and 2p orbitals to get 4 orbitals that each have 1 electron in them. So that's what our hybridization is going to be. Let's talk more about it. So some of our atoms will hybridize their orbitals in order to maximize stability in bonding, right? The only reason this happens, the driving force, is to lower the energy of that atom to create a more stable arrangement. We're assuming that everything is going to defer to the lowest possible energy level. And so things will occur to make that happen. So more bonds are always going to mean more orbitals being filled with 2 electrons, and that brings stability. Much like having a filled octet on a single atom will give it the same electronic structure of a noble gas, and that gives it stability. Forming these bonds to achieve full orbitals in the valence shell will create stability for these bonding atoms. So hybridizing is going to be the mixing of different types of orbitals in the valence shell. So we're just looking at the valence shell. We're not pulling in anything from the core electrons. They're all paired up, hopefully, to make a new set of orbitals, and they're degenerate. And remember, that word really just means that they are at the same energy level. Now, the same type of atom can have different types of hybridization. It can hybridize just one s and one p orbital together, or it could take an s and two p's or an s and three p's, and it's going to hybridize a number of orbitals to maximize bonding. So it's going to depend on the atoms that it is interacting with to form covalent bonds too. So the standard here is that the number of standard atomic orbitals, so our s, our p, our d, that combine is going to be equal to the number of hybrid orbitals formed. So if I put in one s and one p orbital into my hybridization scheme, I'm going to get out 2 sp hybridized orbitals. Let me draw a picture of this. So I really like looking at things on an energy scale. That it helps me for some reason. So I'm going to take my 2s and my 2p orbitals for carbon. And so I've got these 2s and I've got these 2 here in the 2p. What it means to hybridize orbitals on a carbon is to choose 2 of these atomic or 3 or 4 of these atomic orbitals and combine them into a hybridized ones that'll be at the same energy level. So let's just do the simplest sp. So we're just going to take an s orbital and a p orbital, and we're going to hybridize these 2. And when we do that, we're going to have them hybridize at an energy level that's kind of in between the 2. So I'm going to take a higher energy orbital and a lower energy orbital and hybridize them, combine them. So they're going to have an energy that lands kind of in the middle, something that's essentially like the average of them. And so this is going to lead to 2 orbitals that are sp hybridized. Now, the p orbitals still remain. Let's do it like this. Like they haven't gone away. So we still have 2 p orbitals left over. And so if I sp hybridize something, I'll have 2 hybridized orbitals in the atom and 2 normal atomic orbitals still. And for carbon, if I'm going to then place my electrons here, I've got 4 electrons. We still use the off-bow principle. I would have 1, 2, 3, 4. Well, we would need them unpaired. It would probably be like this. 1, 2, 3, 4. These come up closer in energy, so it's easier to have them all be single. All right, so let's look at this for something that's tetrahedral. Now we're going to kind of walk through this in more detail for each of these. So here's that another way to kind of draw. I like using the energy scale to differentiate the difference between S and P and to explain why the energy for the hybridized orbitals are kind of in between them. But this is just looking at them as degenerate orbital diagrams, which is So if I combine all of my s and p orbitals in carbon in the valence shell, I would get sp3 hybridized. I'm taking 4 total orbitals, atomic orbitals, and I'm going to get out of it 4 hybridized orbitals. And now I'm going to fill one electron across because these are all at the same energy. Before I put 2 in my S2s because it was at a lower energy than my P, so I would fill those completely first. Now that everything's at the same energy, I'll just one electron in each orbital. So that's taking these ones right here. So these are our atomic orbitals, and hybridizing them into 4 new ones. And the shape of them, because we are combining, essentially think for each of these, we're overlapping an s orbital and a p orbital, right? So the space where the phases are out of phase would be a space of destructive interference, right? Not constructive. These are going to get smaller. And so that's going to become this piece right here. And the parts where there's constructive interference will get bigger. And that's going to be this part of the lobe right here. And so we get this picture that looks like kind of a weird, like, it looks like this, right? It's like this disproportionately sized p orbital. And so that's going to be one of our hybridized orbitals. And it represents one sp3 hybridized orbital. And we'll have 4 of these. And so we get this picture right here of 4 of them. And they're going to, this is like, you know, taking up space as a negative electron. It's going to repel from the other ones. So it's going to arrange themselves in space as far apart from each other as possible. And you're going to get this tetrahedral shape where everything's about 109 degrees apart. And so by combining these orbitals and kind of using Vesper theory here too, we're going to get this picture that matches what we actually see experimentally for the shape and the bonding patterns of carbon. And so here's a picture of CH4. I've got NH3 here too. And so these hybridized orbitals can be used for both bonding or just bonding electrons and also for lone pairs. And you can see that right here in our NH3. We hybridize the orbitals, and when we do for NH3, remember N has extra electron compared to carbon. It has 5 valence electrons instead of 4. So thinking about its sp3 hybridized orbitals, if it has 5, it's 1, 2, 3, 4, 5. When it pairs up, that becomes our lone pair on the nitrogen. And then we have the opportunity to form 3 bonds because we have 3 unpaired electrons. And those are going to bond with these hydrogen atoms to spin pair 2 electrons together, one coming from the hydrogen and one coming from the hybridized orbital on the nitrogen. So according to valence bond theory, what's going to happen is that bonding is going to take place between atoms when either their hybridized orbitals or their atomic orbitals interact. And with hydrogen, it just has a s orbital. It can't really hybridize it at all. It doesn't have anything else in its valence shell. So our hydrogen will just come with an atomic 1s orbital to overlap with our hybridized orbital, our sp3 hybridized orbital for either carbon or nitrogen. And so as those interact, they need to be aligned along the same axis so they overlap, or they need to be parallel, like they need to have their orbitals overlap like parallel or perpendicular to one another. So that was a look at sp3 hybridization. Now we're going to take a look at sp squared hybridization. So this is when we're going to take these 2 p orbitals and 1 s orbital and combine them to form 3 of our sp2 hybridized orbital. And note there is still this 1 p orbital left over that's unhybridized. And so when we combine these, we're going to get this picture. We're combining 3 right here. What we're going to do is we're going to see that S overlapping with the P creates that same picture that we saw in our sp3 hybridized. But now with only 3 of these, they're going to arrange themselves 120 degrees apart. Now, that carbon center here with those hybridized orbitals also has, so I'm going to kind of draw them like this. one's coming out at you, one's going back into the plane of the board, there's still an unhybridized p orbital here. And it's, so here's my p, and here are my sp squared hybridized orbitals. And those are all on the carbon, now ready to form bonds that'll be 120 degrees apart with each other. Looking at just sp hybridization, like we talked about before, we're combining just one p and one s to form two of our sp hybridized orbitals, and that leaves two of our unhybridized p orbitals. So when we combine these two together here, we're still getting that same shape again, but we only have two, and so they're going to be 180 degrees apart. And so this carbon here that has these two hybridized orbitals, our s and our p, let me make that green. So we have our hybridized orbitals here. We still also have those two p orbitals. So we've got probably one in one axis and one coming out in another axis. So we still have our two p orbitals. And they're all around that same space. So now this carbon is prepared to bond to two things and then use those p orbitals to participate in double bonds, which we'll talk about a little bit later. So here's kind of the table that shows all of these hybridizations that are possible. Now, it's important to remember that the atomic orbitals used are valence orbitals only. So for a lot of things, like in the second row, that's only s and p. In our first row, it's only s orbitals, so there's no hybridization. But remember how we talked about expanded octets? And once you hit that third row of the periodic table, the valence shell has s, p, and d orbitals. Now, those d orbitals are empty because they're pretty high in energy, and we'll start filling the 4s first, but we have these empty d orbitals that we can hybridize into our bonding orbitals. And so you see this pattern that after we hybridize s with all of our p orbitals, we could start hybridizing with our d orbitals as well. And by pulling in one d orbital, we now have 5 bonding hybridized orbitals, and that's how we get our trigonal bipyramidal geometry. Now, if we pull in 2 d orbitals, we'll have 6 bonding orbitals available, and that's how we create the octahedral geometry that we were talking about in expanded octets. And so valence bond theory then shows exactly how those empty d orbitals are able to participate in bonding covalently when there's no electrons that are occupying those d orbitals.